There you go? Okay. All right, so I'll begin with a word of prayer. Ahem. 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 All right, I'm starting. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. I thank you for their perseverance on the homework. I pray that they did well. I pray that you would encourage them as they work on this course, just to encourage them each and every day just to do their best, Lord. I pray that you be glorified in what we do here this day. Again, Lord, we thank you for your many blessings to us this day. In your name I pray. Amen. All right, so make sure you've turned in your homework. There should be a stack of it up here. So if you haven't already, please bring it up and turn it in. I've got a handout for you guys. So we'll just talk about this. The first few minutes in here. This is from Thomas's calculus. Who is Thomas? He's a guy who wrote a calculus book. I mean, not from the children's show. No train. I know many of you being engineers, you get excited about Thomas, but sorry. I'm not calling you all train drivers. I wouldn't do that. That wouldn't be nice. I say, what's wrong with train drivers? You know? Oh, sorry. Everybody got one? So this is what I was foolishly attempting to communicate to you at the end of last class. It's just that, essentially, if you have a, what is a quadratic surface, or a quadratic surface, as some people say? It's something, let's see, basically of the form ax squared plus by squared plus cz squared plus dxy plus exz plus fyz plus gx plus hy plus iz equals to k. So if you have a solution set of that form, it's a quadratic surface. And it turns out there's a lot of possibilities in such an equation. I mean, a, b, c, d, e, f, g, h, i, and k are constants, all right? So as you look at this handout I just gave you, first of all, we see that we get an ellipsoid, right? When we just have the first three terms and the rest of the stuff is gone, right? We can get an elliptical cone. We can get a hyperboloid of two sheets, a hyperboloid of one sheet, an elliptic hyperboloid, elliptical paraboloid, a hyperbolic paraboloid. We have all these interesting different shapes, all obtained, right, from just different cases of this kind of equation, right? A lot of these are called conic sections because if you take a cone and you slice it with a plane, you can get, those are, I'm talking about curves there. Conic sections are parabolas and hyperbolas and circles. Now, here, let's make it interesting. Let's flip the other side. Let's do a couple of examples. Suppose we have x squared plus y squared. I'm looking at number 1, 4z squared equals to 10. What is this? In terms of the other side of the sheet, what is this? Mm-hmm. This is an ellipsoid, right? Which is fancy speak for squished sphere. Now, let's look at another example. How about number 3? There we've got x is equal to y squared minus z squared. You're not going to find this on the other side, I don't think. This is not not the standard, like a lot of times the sort of standard version of this would be something like z is equal to x squared minus y squared. It's like that. with x playing the role of z. Yes, sir? I keep turning to the same side of the page. I've got a stack of these. When you say example 5, what do you mean? Oh, yeah, okay. You're saying something. Okay, yes, thank you. That is number 5. Good, true, yes. Very good point. So what is it? You said a hyperboloid?
Yeah, I think it's just a hyperbola that's going through space along the x-axis.
Right, so if we fix x equals to x naught, what do we have? We've got x naught is equal to y squared minus z squared, right? And so if you think about that x equals to x naught plane, right? You've either got one of these guys, right? Or you've got one of these guys. It's a hyperbola. It's a hyperbola. So a picture of what that looks like when you put it all together is in the lower right hand. It's the hyperbolic paraboloid, I believe. See, the equation is y squared over b squared minus x squared over a squared is equal to z over c. So it's like this. This is in fact a hyperbolic paraboloid. The reason I gave you this handout is so that I wouldn't be so foolish as to try to draw that thing today. There's a select subset of days I can draw that. This may not be one of them. I don't want to find out. It's here. But you got to imagine, instead of z, the axis is x, right? X is playing the role of z. And, well, I guess y is playing the role of y. So, but the role of x and z have been flipped. Okay? Let's get another one. Oh, I do mean for everybody to have one. I do. I tried to ask that, but I did not ask it forcefully enough. All right. Hey, you guys, which one do you want to look at? You pick it. Which one? Let's do one of the even ones. 10? All right. So here we have z is equal to minus 4x squared minus y squared. Indeed, this is an elliptical paraboloid. Yeah, it opens down. Let's look at that in some detail, okay? So how do you if suppose you don't have this sheet in front of you and you need to figure out what the thing looks like from base principle, how do you do it? I do give you guys a 3x5 card for the test, so these are the kinds of things you can scribble in your size 4 font into the margin, I mean, I would put that there if I was you. I don't find memorizing the names of these things particularly exciting. I mean, I happen to know them, but if you look at, let's just look at a specific example. What if you look at 1 equals to minus 4x squared minus y squared? That looks like it might be a level surface, right? Or, excuse me, a level... I'm thinking z equals to 1, right? So this would be like the intersection of the z equals 1 plane and this elliptic paraboloid. What's the solution set to that equation? It's a trap. Let me put a few more. How about 0? And then how about minus 1? Each of these things is not like the other. I suppose 2 of them belong. I don't know. No solution, right? Why? you have something, the sum of negative things equals to a positive thing, right? There's no way you can get a solution here because we have negative equals positive. There's no real solution. This, there's one solution. What is it? Right. This guy, you can reformulate as 4x squared plus y squared is equal to 1. And that is what you were pointing out. This is an ellipse, right? So if you're trying to graph this, right, you've got the point at the origin, 0, 0, 0. You've got nothing when z is positive, right? When you get to z equals to -1, you've got some like ellipse, right? And if you keep going down, you've got ellipses. And so it's something like this. I mean, I'm not drawing it well, but you get the idea. Let me draw these dotted behind the thing. So the circle would be for this circle is called a trace. A trace of the surface. You take the surface and you intersect it with a Cartesian plane. In this case, z equals to z naught. That gives you a flavor of what it looks like, right? If you take these horizontal cross sections, nothing, 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 origin, ellipses, 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 bigger and bigger and bigger, bigger ellipses. That's what you can think of as forming this elliptical paraboloid. It's just a stack of ellipses getting bigger and bigger and bigger. And the reason it's called a paraboloid is what? Why is it called a paraboloid? Why paraboloid?
Because it's a shape built out of parabolas?
Yeah, if you look at the curves, which I'll now foolishly try to draw in purple, these guys are actually parabolas. If you were to draw a vertical cross section, right, like this, you'd find that this is what it looks like. For example, just to be more specific, if we look at the what, for example, the y equals 0 is the what? The xz plane. What is this? What does the elliptical paraboloid give us in this plane? It gives us a curve, right? What curve does it give us? It gives us z is equal to minus 4x squared minus 0, right? In other words, z is equal to minus 4x squared. Sorry, guys, I should warn you, my z sometimes degenerates into a cursive z. Those are not to be distinguished in this course. They are equal. It's hardwired. I can't fix it at this point. It's an unfortunate thing. If you're reading a solution of mine and I go from script z to like the z I just wrote there, don't assume it actually is a different variable. It's probably the same variable. This is much akin to the problem I used to have with some Greek friends of mine. I would be reading something, they'd have like 4a squared is equal to 1, and then the next step they'd have like alpha squared is equal to 1/4, and I'd be like, what happened? And I'm like, is it a or is it alpha? And they'd be like, yeah, it's alpha. It's like, well, they're Greek. A is alpha to them, right? So that's how it is with the z and the script z for me. It's not a good thing. It's just a thing, okay? Just to warn you. Fortunately, not a problem with my type notes, but anyway. Did you see why it's called a paraboloid? An easier example is something like this. Z is equal to x squared plus y squared. Here, I'll do it plus 1. I took the paraboloid and I shifted it 1 unit up. You can do games like this. So if I were to be so foolish as to draw that, the smallest this is 1. And then it's like, just opens up like that. I would also call that that's actually would be a circular paraboloid, right? Because the cross sections would be circles. If I look at z equals to a constant, the intersection of this and the surface and that horizontal plane would be a circle. Everybody with me? So how do we parameterize these things?
Question?
Yep.
The exercise here is to match them with the shape. You just match it all. Which shape is it? Is it K or L?
Which one are we talking about?
For example 5, going back to example 5.
Because we can't decide. We don't exactly say.
Example 5.
Is it K or L?
I hear you. To make it make more sense, let me draw something up here. Let's see here. So if I'm so foolish as to try to draw it. Oh man, I was trying not to draw this. What you guys doing to me? X. Smarter thing to do would be just to take the picture in the page and relabel the z to x and the x to z. Oh well, I'm not that smart. Okay, so K or L, you say? All right, so if it's K, if we look at a cross-section with z equals to a constant, what should we get? So here's, roughly speaking, a picture of K. It looks like this, right? My point is up here, if you look at z equals to some constant, like, I don't know, 3 or something, you should get what? Some kind of parabola? Something along the lines of, this is x, right? So it should be something like, x is equal to, I don't know, some number, let's say k, minus some other number, whatever, L times y squared. Because it's like it's opening down in the x direction, and y would be the variable here. So I would expect the curve of intersection with something like that. So if I take 5, if I take number 5 and I think about it, number 5 was x is equal to y squared minus z squared, right? And I put z equal to 3 or something, right? That gives me x is equal to y squared minus 9. So it is not k. It must be the other one, I think. But I could be visualizing it wrong. Let me think about that. Yeah, I just have a hard time visualizing L personally. Yeah, this is L. It's L, yeah. Yep. Yes. Yeah, you need to be able to construct basic quadratic surfaces from these equations. That is true. Because if you can't do that, then you can't do integrals later. So it's something you want to work on. I try not to ask anything. I try to steer away from these because of, I think these are nasty, but these are decent questions because I think everybody can visualize bowls that open up or open down. It's not too bad. I will agree with you that this is a monstrous beast to try to picture. So, what was the question? No? But anyway, I mean, more to the point, you can look at old tests that I've given before to kind of get a better sense of where it is that I actually test on. I think the more interesting question is, what are these things, right? And how can we understand them? So let's get back to that. So the one principal tool we have is to look at the the way these surfaces interact with x equals to a constant, or y equals to a constant, or z equals to a constant, right? Those are called traces, and as you can see, we get a lot of information about what they look like from those. Okay, so how do we parametrize these? So guys, let me start back. Okay, so let's see here. An example. How about a cylinder? X squared plus y squared equals to, 4. How would you parametrize this? And let's make it simple. Let's say 0 is less than or equal to z is less or equal to 3. What would the parameterization be of this? How would you do that? So let's see here, 2 cosine, let's say t, 2 sine t. That puts me on the cylinder, right? And then if we just let s go from what? 0 to 3, right? That will be a parameterization for this cylinder, without the caps, of course. Yes, sir?
How did you get that?
Oh, that's like asking, how did I invent a new recipe? Or, I don't know. Parameterizing things is an art.
To answer your question, though, I looked through the notes, so I knew that was kind of the format he was looking for. Cheating.
If you have, there are some rough guidelines. If you have a sum of squares in here, sine and cosine are your friend. If you have differences of squares, caution cinch. If it's something truly oddball, you can go back to trying to solve for a Cartesian equation and deal with the roots. But that's really admitting defeat. If you have to go back to these Cartesian equations and there's square roots and you face plus minus issues, that in some sense or another kind of means that things didn't go well at the office. It's not ideal. You don't want that. You want to use sine, cosine, caution, cinch, if you can. Okay, so now what if that would get the whole cylinder, right? If I do what? 0 less than or equal to t less than or equal to 2 pi goes all the way around. 0 less than or equal to s less than or equal to, I said 3. Yes?
So do we just make up anything for that then? Because I'm really lost as to how you got the parameterization.
Right. I'm going to give you a list of examples. As the examples go on, it should start to make more sense. I can't give you like a big picture drop down, put the example in, here comes the answer out. That would be a really, really complicated thing to try to write down. It's better to show you examples. Eventually, it starts to, For example, what if I was to give you this one? What if I said y squared plus z squared equals to 9, and 0 is less than or equal to x is less than or equal to 1? Could you, from this example, tell me what to do here? I'm going to do the easy part. I'm going to put the s here because I'm going to let x just go from 0 to 1. I could even just say I'm going to use x as one of the parameters. I could put an x here and an x here if I wanted. But so how do I get y squared plus z squared equals to 9 using some formulas? 3 cosine t, yeah. And 3 sine t, yeah. So if this is y, and if this is z, right? If you calculate this squared plus that squared, you get 9 sine squared plus cosine squared, which is 9. So it solves the given equation. So again, the problem statement is this. Here's a surface presented as a level surface. Find the parameterization, okay? That's the problem we just did. We can do a little bit more with these examples. What if you don't want the whole cylinder? What if you just want a half of the cylinder? How would you get just a half of it? Yeah?
So it will limit the values which t can take.
Right. So up in this one, if well, that is annoying. So if this is x and this is y, all right? So this vertical line here is what? What parameter value is that vertical line there? In terms of s and t, what is it? S is free to vary from 0 to 3 on that line. S varies along that dotted vertical line. What's the value of t there? T equals 0. Does anybody disagree with him? Listen, there's another way you could think about these if you have a piece of paper, right? Basically, you can think of this being the s direction, this being the t direction, and we're just wrapping it around like that, right? So the place where it glues together is where the t equals 0 and t equals 2 pi glues together. So this is actually t equals 0 and 2 pi. It doubles up on that gluing point. Yeah.
All cylinders are just t 0 at that point, or only cylinders centered on those points on the axis?
It depends on the formulas you're using, but we always have the fact that sine and cosine loop back to where they started. It depends on how the formulas are set up. Yep.
The 2 pi part, do you give it? Like, is that given to us, or do we just know that?
You know that from what you know about sine and cosine, right?
Okay.
For sine and cosine to go all the way around the values, they have to go from 0 to 2 pi. There actually is an even better answer to this as soon as we study curvilinear coordinates. So I'm going to suffer through this with you guys a few more examples. Then I'm going to introduce curvilinear coordinates, and then we'll have yet another way of understanding where these formulas are coming from, which might make more sense to you guys. We'll see. So yeah, y is 0 to 2 pi. It's to get the whole thing. Now I could have done minus pi to pi. I could have done 5 pi to 7 pi. Like whatever choice of t that makes sine and cosine go full cycle, we'll do it. If I just want a half of the cylinder, I just chop down the domain appropriately so. So like if I just want, say, this half, like that, then what I would do is I would restrict t. I would say 0 less than or equal to t less than or equal to 2 pi, listen to me, pi. And that would give me just that half of the circle. Well, where is that? How would you describe that in terms of Cartesian equalities? It's what? This is, I would hope it's y greater than or equal to 0, right? See, y is greater than or equal to 0 there. Let's check our work. This is y. This is y right here, right? What can you say about sine from 0 to pi? What's the graph of sine look like? Yeah, it's positive, right? So sine looks like this, right? Here from 0 to pi, it's positive, so that output's positive. As you go from pi to 2 pi, the sine cycles to negative, and that gives you the y less than 0 part of the cylinder.
What if you were trying to cut it the other way,
Horizontally?
That would just mean the d would change?
Oh yeah, we would limit the s value in our setup right now. Okay.
See, he agrees with me.
Oh, you think it's a conversation between me and the heavy equipment? I don't know. Yes, sir.
Can we just do one quick example?
That coffee's old. With a what?
Can we do one quick example
It's there. 0 less than t less than pi. Everything else stays the same.
So your parameterization.
The same formula, you just limit t so that it only lets the y be positive.
Okay. That's what I was missing. Thank you.
It's like in the, think of this as being, think of a paper. You can visualize what's going on in terms of a mapping. So you've got this, this piece of paper, and you're essentially, the parameterization is taking it and is rolling it up into 3 dimensions. And so half of the paper is going on to, I should use different colors. This half of the paper, say from 0 to pi, this is t, this is s. So this half of the paper is going on to that half of the cylinder, right? And then the other half is going over there. It's probably not helping. Oh.
You just change the bound.
Yeah. Yep. If it's the same, if you're just selecting some subset of a given level surface, if you already have equations which go to the level surface, then you can tweak the choice of the parameters to select some subset thereof. Oh. Let's look at a hyperboloid, or, yeah. I might look at a cone later, I don't know. So how about this? X squared plus y squared minus z squared equals to 1. How would you parametrize this? Is that a hyperboloid of 1 or 2 sheets? I hear 1 sheet. Okay. So let's see here. Another way to look at this would be, there's different ways to parametrize it. My inclination is to think, I want this to work out to like a cos squared t. I want this to work out to sinh squared t. So I know that cos squared minus sinh squared is 1, right? So if that's my goal, then what I will do is I will let x equals to like cosine of, I need some other letter, let's say theta, cos t. And I'll let y equals to sine theta cos t. Now, the reason I do that is why. I know sine squared plus cosine squared is 1. So if I give you those formulas, when you say x squared plus y squared, you get what? So, yeah, just you get cos squared t, right? So I'm trying to show you the man behind the curtain at the moment. This is my thinking. I could just write these formulas down and say, memorize this. This is how you parameterize a hyperboloid. But my thinking is to use the known trigonometric identity and hyperbolic trig identity, which is this. So z is what? Just sinh t. Right? And there you go. Those are the parametric equations for this. So r of theta t, cosine theta cos t. That could get annoying. Sine theta cos t and sinh t. If you go back and plug these parametric equations for x, y, and z into the level surface, you'll find that it works. In fact, yes, x squared plus y squared minus z squared works back out to 1 because it works back to cos squared minus sinh squared, which is 1. Now, what if I just wanted to choose the part of this hyperboloid? Now, what does this thing look like? How would you visualize this? Here's how I would do it. This gives me x squared plus y squared equals to 1 plus z squared, right? 1 plus z squared is greater than or equal to 1. So basically, this hyperboloid of one sheet, the skinniest it gets has a radius 1 when z is equal to 0, and then it gets bigger and bigger, insert bigger circles above, and bigger circles below. So if you think about the traces of this thing, it looks something like, there's this radius 1, then up here there's a bigger one, down here there's a bigger one, and bigger and bigger. And the reason it's called the hyperboloid is because there's this hyperbola which connects these circles. Something like, I can't draw it worth anything, but I do better if I try to draw it like this. So the skinniest it gets is z equals to 0. Once you choose a parameterization, a natural thing to ask about is this is actually part of defining it. What are the lines on the surface which correspond to constant choices of parameter, right? So I drew some of those over here. The vertical lines are when the t is fixed at a particular value and the s varies. The circles have s fixed and let t vary. But these are coordinate lines with respect to these parameters. For this thing, what happens if you fix theta and let the t vary? I think those are the ones that kind of go vertically. Like this. So these are from, fixing theta, let t vary. Vary. On the flip side, if I fix t, right, if you put t equal to a constant, that means what? First of all, z is equal to sinh of whatever that constant is. So it's in a plane. And so if I look at t equals to a constant, what is it? Let's say t equals to t naught. What's that give you? Yeah, I get x is equal to cosh t naught cosine theta. Y is equal to sinh of t naught sine theta. And z is equal to, what is it? Sinh of t naught. What is this? I submit to you that this is a circle. It's a circle in the z equals to sinh t naught plane with radius what? Oh. Oh, I was like, that's not a circle. That requires further calculation. No, thankfully I made a typo here. This is supposed to be what? Cosh, yeah. So you see, that's the radius for this circle. The radius is cosh, cosh of t naught. So basically, these circles that wrap around here like this, I can't draw them very well, but the circles those are where the t is fixed and theta varies. The theta varies, you travel around these circles, right? As t varies, you go up and down these hyperbolas. And together, the union of those circles and hyperbolas forms the hyperboloid. And that's the geometric meaning of this parameterization, right? But where did I find the formulas? I didn't find the formulas from thinking about that geometric meaning. I found the formulas from something more basic, which is that I know cosh squared minus sinh squared is 1, and I know that sine squared plus cosine squared is 1, and I just tinker algebraically. Do not dismay. There really is only about 3 or maybe 5 examples here you need to learn. If you just work through them, there's really not that much. I'm not as imaginative as you might fear. Okay. Anyway, we're going to come back to this as later in the course we face these problems called surface integrals. And to actually calculate a surface integral, we actually have to be able to find a parameterization of the surface in order to do the calculation. So in part, I'm talking about that now to lay groundwork for that later discussion, because, you know, you guys have trouble with parameterization. So if you're feeling lost, you're not alone. There's probably at least half of you are lost right now. All right? So the way to become unlost is to work some homework problems. So, but anyway. So I want to show you another way to think about these, which is through what are called non-Cartesian coordinate systems. All right? So let's see here. We have cylindrical coordinates. Right? And we also have spherical coordinates, but I'll start with cylindrical. So the cylindrical coordinates, how does that work? So here's x, y, z. How are cylindrical coordinates related to the Cartesian coordinates? Like if I pick a point, say x, y, z, how is that related to the cylindrical coordinates? What's the definition? Well, you actually already know these things. Basically, you drop the point down to the xy plane, and the distance from the origin there is what we call what? Yeah, that's the radius. This is the polar radius. So that's r. So first of all, and then the angle down here, the standard angle is what's called theta. So we have x is equal to r cosine theta. We have y is equal to r sine theta. Those you can see in the picture. If you look here, this piece, right, and this piece, so that's r cosine theta is here, r sine theta is there, right? Yeah, z is just here, right? Z is z, yeah. Z just stays the same. So in that sense, cylindrical coordinates are kind of friendly. They're at least 1/3 Cartesian, right? So z is z. I'll write it like that there. It's kind of silly, but that's the other part of it. All right. So how are these related? Well, one thing, x squared plus y squared is equal to r squared, right? Now, if I asked you, what is x equal to a constant, was y equals to a constant, what does z equals to a constant mean in Cartesian coordinates? By now I hope you realize those are horizontal planes or vertical planes, right? But all of a sudden, in the context of cylindrical coordinates, if I ask you what does it mean to freeze one of those variables, it's interesting. Well, z equals to a constant, that's still a horizontal plane. What is theta equal to a constant, though? It's actually a half plane. I'll just draw it up here, but it goes down and it goes up, right? It's an infinite thing, and it goes on and on and on. But it's a half plane because it's just a half. It doesn't go the other side. Yes, sir.
How would that work? Does r have the possibility of being negative?
No, we insist that r is positive here. Yeah, I know in calculus too, sometimes it's convenient to let r be less than 0 for the sake of making those polar graphs and stuff. But we will insist that r is non-negative, as to not go nuts with the identifications. I don't know. There's probably some homework problem somewhere where that could be relaxed for your convenience. I wouldn't deny you that. But as far as I'm talking, if I'm talking about r is non-negative, okay? I know if you identify minus r with the pi angle, it's convenient sometimes, but that's a half plane, right? How about, what if you look at r equals to a constant? What's that? All right, that's a cylinder with radius r naught. So what if you want to parametrize a cylinder? So in terms of cylindrical coordinates, to parametrize a cylinder, if I have x squared plus y squared equals to 4 and I want to parametrize it, I can say, aha, well, this is really just r squared is equal to 4. We choose r to be non-negative, so this is really just r is equal to 2. So one of my cylindrical coordinates is frozen, and I can just use the usual cylindrical coordinate transformations to define the parameterization. I have x is equal to r cosine theta. I have y is equal to r sine theta. I have z is equal to z. Leave z alone. All right, it's there. R is 2, so this is 2 cosine theta. This is 2 sine theta. I don't know, maybe I should start with this and not even tell you guys about this, because it seems to confound some of you, this way I have of thinking about this. I don't know. I don't want to confuse you guys, but there's always some subset of students who doesn't know what I'm doing over there. So anyway, this then gives me the parameterization, right? I can use r of theta z, 2 cosine theta, 2 sine theta, z. There you go. That's the parameterization for that cylinder. If your surface is related to one of the standard coordinate systems by just freezing one of the standard coordinates, it's really easy to write down the parameterizations. You can just use the standard cylindrical. Oh man, that's got a terrible glare. I hope the glare isn't messing up the camera. Could you just, thank you. Thanks. What if you wanted to parameterize a half plane? What if you wanted the parametric formulas for a half plane at 45 degrees? All you do, what would you do? What would you use as your parameters in this case? The easy choice. Everything except for theta. What's left? You got r and z, right? Sometimes I use a capital X for the parameterization when I don't like to use r 2 different ways. So I could use a capital X if I wanted, or hourglass, as you guys can call it sometimes. So that's r cosine pi over 4, r sine pi over 4, and z. And there you go. That is a parameterization for a half plane. It's been a long day for me, but it didn't take me much mental energy to write that down, right? I could do like 20 more of those and not need coffee. Yes, sir?
Yeah, what goes in the parentheses?
I'm always going back to the standard, the relation between the Cartesian and the polar coordinates. X equals r cosine theta, y equals r sine theta, z is z. Well, I put theta equals to pi over 4.
Right.
So this is r cosine theta.
No, I'm talking about capital X, and then you got your r z.
Oh, these are the parameters. Geometrically, what's going on here? Here's your half plane, right? If you look at this, z, right? Here's z equals constant. These are lines where z is equals to constant, r is varying. And then these guys is when r is constant and z is varying. Those are your parameter lines. Those are your parameters. You give me a specific value of r and z, it picks out a specific point on this half plane.
Okay. For like your question would just be parameterize a half plane at theta equals 4, and then
Right.
like r and z are the only two that could be there. Is that what it is?
Oh, there are infinitely many choices. It's like asking, what pictures are you going to paint today as an artist?
Why did you pick iron and Caesar?
Because I'm a boring artist. And I wanted to use the same trick I just used in the last example, which is to freeze one of the cylindrical coordinates to let the other two to be the parameters. Let me show you more examples of this idea. Unfortunately, I don't have hyperbolic coordinates, so this example never really gets much better than it is. All right? But there are a few surfaces which appear in the study of spherical coordinates, which are really, really nice. So, spherical coordinates. I introduced these earlier than a lot of people simply because I think the longer they have to set in, the better. And if you can use spherical coordinates to simplify a problem, it's definitely worth your time. So here's the way spherical coordinates work. Pick a point, x, y, z. And we still use theta. Theta is still theta. All right? The spherical radius, we use a rho for this. So, this is RHO, rho. That is the square root of x squared plus y squared plus z squared, okay? It's actually the distance from the origin, the spherical radius. Theta is the standard angle, right? The angle off the z-axis, all right? We denote phi in mathematics. So this angle here is called phi, right? So if that's phi, right, this is a right angle. There's two parallel lines, the z-axis and this projection of x, y, z down onto the plane, right? These are parallel lines. Can you see that? So we have opposite interior angles. You should be able to see that the angle phi is also up here. So if this, right, is the hypotenuse of this right triangle, let me just draw it over here. So here's the triangle, the vertical triangle with the right angle, all right? So just to match it up, okay? This hypotenuse is rho, this angle's phi. What's that make the double dash? Rho sine phi, yes. What else is that in terms of the cylindrical coordinates?
R.
Yes, that's equal to r. By the way. But anyway, so what we just found, if I can find a marker that works, it was we found that this guy right here is rho sine phi. So now you can look at this blue right triangle down here where the hypotenuse is rho sine phi, and that angle's theta, right? So what does that give you? That gives you rho sine phi sine theta is y, and over here you get rho sine phi cosine theta is your x. And there you have it. Those are the spherical coordinate transformations. X is equal to rho cosine theta sine phi. Y is equal to rho sine theta sine phi. And z is equal to what? This is z here, right? What is it equal to? You know, right? What is it? Yeah, cosine, right. Rho cosine phi. So this is rho cosine phi. So z is kind of not as nasty as the other two, but there it is. And these are the beloved spherical coordinate transformations. Now, to be clear, I mean, there's different choices, but here's one choice. 0 less than or equal to theta less than or equal to 2 pi. But the phi is not like the theta. It just goes from 0 up at the z-axis down to pi at the minus z-axis. So on the other hand, we have 0 less than or equal to phi less than or equal to pi. So these angles are not equivalent. The phi is a direction angle. Phi is a direction angle off the z-axis, right? Theta is not a direction angle. Theta is the polar angle, the usual thing. So what would I ask then? There are then 3 variables, 3 different parameters, 3 different coordinates here you can freeze and ask what the geometry is, right? If I freeze rho, what do I get? Yeah, it's a sphere. So on the sphere, I would use what as parameters? I use theta and phi as parameters. If you go back to my last lecture, the thing I put in the box, the thing I wrote down from the thin blue sky was exactly that. Just using spherical coordinates. That's what it was the man behind the curtain, if you will. So, x is equal to r cosine theta sine phi, y is equal to r sine theta sine phi, z is equal to r cosine phi. There you go. Those are the parametric equations for a sphere. Yeah? Now, how about theta equals to theta naught? Still a half plane. Right? Been there, done that. It's the same theta as the cylindrical coordinate theta. Right? But the new one that's interesting is phi equal to phi naught. What's that? Can you see it? It's a cone. Right. So x equals to rho cosine theta sine phi naught. Y is equal to rho cosine sine theta sine phi naught, right? Z equals to rho cosine phi naught. These are the parametric equations for a cone. What are the parameters? Rho and what? And theta. Mm-hmm. Nah. Well, I don't know. I mean, it depends on what you're looking at.
Okay.
It will matter to us later. I try to put phi then theta for reasons that I'll explain later. But I'm programmed to put theta then phi because that's what I was taught in physics. And here's the annoying thing, guys. In engineering and physics, the meaning of the theta and phi are reversed. And to make it even more fun, sometimes rho is replaced with a lowercase r. But then oftentimes the r is replaced with a lowercase s. Anyway, the bottom line is you should try to think in concepts, not notation, and then you'll be safe from these kinds of things. Let's investigate the cone further, if I can. When's this class end? 5. Oh, right, we got plenty of time. Woo! So I just gave you these allegedly parametric equations for the cone, right? Geometrically, you believe it, right? I mean, if you look at the cone, it's always a double cone, by the way, right? Well, is it? I don't know. That's a good question. Is it a double cone with? I think it's not a double cone if we use the phi equals to phi naught. I think that's that.